This video is just a brief review or overview of complex numbers. Here I'm assuming that you've seen complex numbers before, and I won't be going through any detailed concrete examples because, again, I'm assuming you've seen a lot of this before. The main point is just to go over notations and different viewpoints. So let's get started. One way to define the complex numbers is just to declare that we have this number I, which when squared gives you -1. So since you can't do this in the real numbers, we have something generally different than the real numbers, and we define C, the complex numbers, as all formal combinations of x in the real numbers plus I times y, where y is also a real number. So as a set, this looks just like R2, and we're going to be talking about how it compares to R2 in the next slide. But the way you add is component-wise, so the real parts, x plus yi plus u plus vi, you just add the real parts, x and u, and you add the imaginary parts, y and v. Multiplication is just basically rigged to be distributive, so you multiply everything out just as you would with real numbers, but you have to include our condition that I squared is -1. So you get the following as our definition of multiplication. And then something you show is that, well, the complex numbers become a field with addition and multiplication as we've defined them. So we have basically my dear Aunt Sally, the multiplication, division, addition, and subtraction. And multiplication is commutative. You can see that by just staring at the formula, where you can switch x and u, y and v, x and v, y and u in this formula, and you get the same thing. On this slide, we're going to go through comparisons between R2 and the complex numbers, just to see the significance of some of the operations on complex numbers and hopefully give you some indication why complex numbers can do more for you than just the structure of R2. So points in R2 are represented with an ordered pair x, y, and points in C are also an ordered pair, but we write them this kind of special way because, again, we have this multiplication where I squared is -1. Addition, as we already defined it, is just component-wise, and so in R2 you can think of that as vector addition that you learn in calculus, tail-to-tip addition of vectors. So in the complex numbers, you have the same thing going on. The multiplication, obviously, is a little more interesting. When you multiply two complex numbers here, a plus bi times x plus yi, we got this formula before. And in R2, you can view this as a linear transformation because the first component is ax minus by, and the second component is bx minus ay. And you can convert that into a matrix computation. So this matrix here times the vector xy will give you the two components that we had over here on the right. And you could even expand this into multiplication of two matrices. And these matrices have a special type. Obviously, you have A on the diagonal, B and minus B on the off diagonal. And these matrices have a special property that they're conformal, except when they're 0. So conformal here means that they are angle and orientation preserving. And there'll be a homework exercise for showing that. Now, another operation that we have for the complex numbers is conjugation. So to take the conjugate of a complex number, you send it z, written as x plus yi, to z bar, and you replace I with minus I is basically what happens. And the reason this operation is significant is because I is one square root of -1, but also minus I is a square root of -1. And since they satisfy the same algebraic rules, any formula you have with I in it should, generally speaking, the same formula should hold if you replace all the i's with minus i's. And that's one way to justify this, that if I multiply two complex numbers and take their conjugate, it's the same as taking their conjugates first and then multiplying. Conjugation corresponds to reflection across the x-axis, and that's important to keep in mind just when manipulating these. But this multiplicative property is probably harder to think about in terms of R2. Another important operation on both sides, R2 and C, is taking the length or modulus. So we use the same norm notation for the modulus, and it just means take the square root of x squared plus y squared. One nice thing about the complex numbers is that the modulus can be computed algebraically using the conjugation operation. So z times z bar gives you the modulus squared, and that turns geometric questions into algebraic questions, I suppose. And you don't have the same thing over here in R2. The complex numbers, you can take 1 over a complex number. And one way to do that algebraically is to compute z bar divided by the modulus squared. And you could just check directly that z times this formula will give you 1, and that's why it's the inverse of z. Of course, you do need x squared plus y squared non-zero, which is the same as assuming that z is non-zero. We also have polar coordinates in both sides. So in R2, you think about expressing xy as its length times cosine of the angle it makes with the x-axis, and r times sine of the angle it makes with the x-axis. And you can do that over here with the complex numbers, but what we'll do eventually, and I'm not going to dwell on this here because we'll talk about exponentials later, but you define e to the I theta, and we'll do this later with power series, so we don't have to go into much depth about this right now, but e to the I theta will be equal to cosine theta plus I sine theta, and so you can write a complex number in polar coordinates in this more compact way. Okay, in R2 you have a projection to the x-axis where you send xy to x. And that's the same as taking the real part of a complex number, which is important to point out. You can express this using z and its conjugate. Z plus z bar divided by 2 gives you the real part. You also have a projection to the y-axis called the imaginary part over here on the complex side. And you can compute that using conjugates, z minus z bar divided by 2i. And the axes in R2 are the x-axis and the y-axis, and we're just going to use the notation r for the x-axis inside the complex plane. So we think of this as sitting inside of C, and we also have the y-axis in R2, which we'll think of as IR sitting inside of C. The last thing I want to mention in our brief review of complex numbers is just a few additional facts which don't fit in under the last slide of comparing R2 and C. So the first thing I want to mention is that taking modulus is actually multiplicative, and this follows because conjugation is multiplicative. So since we have that ZW squared is equal to ZW bar, and since conjugation is multiplicative and complex multiplication is commutative, you can adjust this into ZZ bar, WW bar, so no big deal. And the next fact is similar. You can expand things like z plus w modulus squared simply because this is equal to z plus w times z plus w conjugate. One thing I didn't point out earlier is that conjugation also distributes with respect to addition. So the conjugate of z plus w is the conjugate of z plus the conjugate of w, and you would just distribute this to get the formula up above. I guess you get z squared plus zw bar plus z bar w plus w squared. The main point now is that zw bar plus z bar w is zw bar plus its conjugate. So this ends up being twice the real part of zw bar. We could have also written it as twice the real part of z bar w, because the real part of a complex number and its conjugate are the same. Okay, so you can expand z plus w squared, and this gives us an easy way to prove the last thing, which is the triangle inequality. So how do you prove this? Well, you expand z plus w squared as above. And the one thing we need to recall or remember is that the real part of z, which is just x, well, that in absolute value is going to be less than or equal to just the modulus of z. So all I'm doing here is just using this easy fact that x is less than or equal to the square root of x squared plus y squared, because the y can only make it bigger. So then here you plug that in. And you get this formula. Of course, we can take the conjugate out because this is multiplicative and the conjugate doesn't change the length. So this here can be factored into modulus of z plus modulus of w all squared, because when you distribute this, you get the formula above. So now we have a square here and a square here, so we just take square roots to get the triangle inequality. So the homework will have a bunch of exercises where you use these facts and other things we've reviewed to prove more detailed formulas and inequalities.